All right, hi everyone. Before continuing on, I actually thought it might be worthwhile to talk just a little bit about what the answer to this problem would have been if we would have used integration instead. So just bear with me here. Let's do that. I think it would be worth it for us to compute that way as well. Okay. So the probability that 3 is equal to or less than y is equal to or less than 8, okay, is going to be equal to the integral from 3 to 8 of f of y dy. Okay? Now, the issue with that is the function itself, remember, the definition of the function itself changes at y equal to 5. Yeah, so from 3 to 5 you would be using this one, and from 5 to 8 you would be using the second definition right here. Okay, so that makes things a little bit trickier, but all that means is that I basically need to break up this integral at 5 and do it in a sequence of 2 integrals, from 3 to 5 and then from 5 to 8. All right, so here we go. This is equal to the integral from 3 to 5 of f of y dy plus the integral from 5 to 8 of f of y dy. Okay, and we actually know what the definition of f of y is on the interval from 3 to 5 and from 5 to 8. Slightly different, but we know how to do that, okay? All right, so let's see here. From 3 to 5, it's equal to 1/25 y. So this is the integral from 3 to 5 of 1/25 y dy plus the integral from 5 to 8 of, okay, so what is it there? From 5 to 8, it's equal to 2/5 minus 1/25 y. You can kind of see that on the notes right there. 2/5 minus 1/25 y. 2/5 minus 1/25 y dy. Okay? And now we need to integrate this thing. Okay? Here, I'm going to bump this down a little bit here. Okay? So there we go. So let's do that, okay? So let's actually do this integration. I thought it would be helpful just because, I don't know, I mean, maybe you haven't done some integration in a while, okay? So this will just dust off the old cobwebs a little bit. Okay, so the antiderivative of 1/25 y is 1/25 times 1/2 y squared. So it's going to be 1/50th y squared, evaluated between, okay, we're using the fundamental theorem of calculus here, evaluated between 3 and 5, okay, plus the antiderivative of 2/5 is just 2/5 y, okay, so this is 2/5 y minus, okay, I don't have to really even think about this, we just do this antiderivative in the same way we did this one over here, except there's a minus sign attached. So it's going to be minus 1/50th y squared, and this thing is evaluated between 5 and 8. Okay? Okay? So far so good. So in the end, let me just kind of erase this. I'm going to copy this down right up here, and then we'll just compute this. We'll compute this thing together. Okay, so this thing is equal to 1/50th y squared evaluated between 3 and 5 minus 2/5 y or plus 2/5 y minus 1/50th y squared evaluated between 5 and 8. Okay, I'm just simply copying that down. Okay. And let's see what happens here. Well, 1/50th 5 squared minus 1/50th 3 squared. So that's going to be 25 minus 9 over 50. Okay, plus, all right, so this one's a little bit more interesting. What are we going to have here? 2/5 times 8. Okay, so that's, so 2 times 8 is 16/5. Minus, okay, 8 squared is 64/50. Okay? Minus, remember you always go evaluate at the top minus the thing evaluated at the bottom. Minus 4/5. Oops, what am I saying here? This should be 2 times, this was 2 times 8, which was 16. Down here it's 2 times 5, which is 10. So it's minus 10/5. Okay? Minus, what's this going to be? 25/50. Yeah, because it's 5 squared. Okay, so what do we end up with here? Well, 25 minus 9, that's 16. Okay, I'm going to draw a huge fraction symbol here. Over 50. Okay, the things over 50, okay, let's see here, plus, okay, to make this 50, I would need to multiply this by 10. So this would be 160 over, this shouldn't be 15, this should be 50. Okay, so this is 16 over 50, this is 160 over 50, minus 64, okay, minus, okay, so this is 10/5. To make this 50, I need to multiply and divide by 10, so it's 100. So it's minus 100, okay? And then it's plus 25. All right, so let's see here. This is equal to, okay, 100 minus 60 minus 100 is minus 4. So this is 16 minus 4 plus 25 all over 50. Which, by the way, is 12 plus 25, which is 37 over 50. Which is exactly what we got doing it the other way as well. So again, we could have integrated and ended up at the same place we did by just using basic geometry. Okay, so just wanted to point that out. Okay, that's that for now. Let me kind of scrunch this up to the side. And we'll start going through this lesson again here. Okay, so we'll move this, put this in the background. Now I want to talk about, just like in the case of discrete random variables, in the case of continuous random variables, we're interested in certain distributions as well. The first one, the most basic one, is the so-called uniform distribution. And that just means you're equally likely to be anywhere in the interval in question. So uniform distribution on the interval from A to B just means that x is equally likely to be anywhere in that interval. Okay? Well, if that's true, then the distribution couldn't look like it did in this example, because it looks like in this one, you know, this distribution kind of spiked up in the middle, which made it more likely to be in the middle somewhere than it would be over here. I mean, there's less area accumulation down here and up here than there is in the middle. So this distribution says that the random variable is more likely to be kind of in the middle somewhere than it is on the edges. With a uniform distribution, that's not true. It's equally likely to be anywhere. Okay, so let's think about that for a minute. Okay, I say on this slide that the density, okay, the density is given by f of x equal to 1 over b minus a for x between a and b. Okay, well, what does the graph of that thing look like? And incidentally, for a uniform distribution, what we usually write is x distributed as uniform AB, or whatever the interval is that you happen to be on, okay? It wouldn't even really matter if you excluded one of those endpoints, because again, it's the probability of being equal to any value is still 0. Okay, so what does the graph of this uniform distribution look like? Well, it looks like this. Okay, so like here's A and here's B. That thing says it's equal to 0 anywhere outside of that interval. So it's just 0, 0, it's 0 everywhere outside before A. But then once you get to A, it jumps up to 1 over B minus A. And it stays there the entire time between A and B. That's just a number, 1 over B minus A. It equals that the entire time between A and B. And then after that, it's 0 again. Okay, so first of all, is it clear to you that this thing integrates to 1? Well, look, this thing is just a rectangular density. And what is the area under here? What is the area under that curve? Well, the area of this is equal to, well, for crying out loud, the height is always 1 over B minus A. The height of this thing is 1 over B minus A. And what is the base length of this thing? Well, it's B minus A. And this is just a rectangle, so it's going to be base times height. So it's going to be B minus A times 1 over B minus A, which is 1, which is exactly what should be true. Okay? So a density that is at the same height everywhere is basically saying the random variable is equally likely to be anywhere in here. Okay? The mean is, not surprisingly, right in the middle of A and B. It's A plus B over 2. We'll talk about that a little bit more later on when we start talking about expected values in the continuous case. Sigma squared, which remember that's our notation for the variance, is B minus A squared over 12. There is the moment generating function. I'm not going to explain that right now because as of right now, I still haven't defined how to compute like the expected value of anything. And remember the moment generating function, in the discrete case, we needed to know how to do expected values. Okay, and of course the mean, mu, is the expected value of the random variable, but we'll talk about that later on. Okay? But the whole point here is that in the uniform case, somebody hands me an interval that happens to live inside of, A to B, then the probability of being in that interval is basically just the proportion of that interval over the whole interval itself. And we'll see that here in practice in just a second. Here's an example. X is time in minutes for a lab assistant to prepare the equipment for a certain experiment. Okay, it's believed to have the uniform distribution where on the lower end it's 25 and on the upper end it's 35. Okay, so I'm just going to erase this stuff and keep the picture basically the same. Okay. And what's our A and what's our B in this case? Well, A is equal to, they say capital A, I'm going to write A small, 25, and B is equal to 35. Therefore, 1 over B minus A is just a tenth. Okay, in this case, we're a uniform 25 to 35, like this. Okay. What is the probability that the preparation time exceeds 33? Well, let's just imagine that 33 is right here. So exceeds 33 means that you're up here somewhere. That means the probability that that happens is just that shaded area under the density curve. Okay, so the probability that x is equal to or greater than 33. And by the way, it doesn't even matter that I have equals here. I could just say greater than 33. Exceeds 33. In fact, I'll do that. It exceeds 33. Well, that's going to be the integral from 33 to infinity even of the density function, which is, f of x dx. Okay, there's the density function, but we know what the density function is. It's equal to 0 once you get beyond 35, and it's equal to a tenth. It's equal to a tenth between 33 and 35. So this is just going to be equal to the integral from 33 to 35, 1/10 dx. Okay? Because everything above 35, that's 0. So it just kills the integral. Okay? All right. So what is the antiderivative of 1/10 dx? Well, it's 1/10 x. So this is 1/10 x evaluated between 33 and 35. Okay? And this is going to be fairly easy to compute. A tenth, 35, minus a tenth, 33. So this is just 1/10, 35 minus 33, okay, which is 2/10. Okay, 2/10. But that's exactly what you would expect, remember? So the probability that happens is 2/10. Okay, which if you look up here, that's exactly what this area is right here. Okay, so this is 2/10. That's exactly what you would expect. Look, I mean, the proportion that this interval eats up of the entire thing, the whole width of this thing was 10, and this is only 2. And it's equally likely to be anywhere in here, so it makes sense that the probability would be 2/10. The height's the same everywhere. So all that really matters is the width of the interval that we're considering, which in this case only has length 2 within the interval that we're interested in, from 25 to 35. Okay? What is the probability that the preparation time is within 2 minutes of the mean? Well, what is the mean of this thing? Well, it's going to be right in the middle. Mu is equal to, the mean is right in the middle. It's 30, right? So it's 25 plus 35 over 2, which if you do that, that's 60 over 2, which is 30, which makes perfect sense, okay? Here is the mean right here, okay? The mean is right here. This is mu equal to 30, okay? 2 minutes of the mean. Well, so 32 is somewhere. Let me move this 33 over. Okay, 32 is maybe right here. Okay, and within 2 minutes, that means I need to go down to 28, all right? So down to, if this is 28 right here, if this is 28 right here, okay, then I'm asking about this. Within 2 minutes of the mean means I'm between 28 and 30, okay? Or 28 and 32, sorry. Okay, so I want the probability that 28 is equal to or less than x is equal to or less than 32. And we don't freak out about equals or anything, okay? And what is that going to be? In this case, it's fairly easy. I could go and do an integral again, but let's not. Let's just say, what is the width of this interval? It's 4. And what is the width of the entire interval in question? 10. It's 4/10 is the answer in this case. 4/10 is the answer in this case. Okay? And this last question right here, for any a such that 25 is less than a plus 2 is less than 35, what is the probability? So that is, A and A plus 2 are both in the range between 25 and 35. What is the probability that preparation time is between A and A plus 2 minutes? Well, okay. Let me erase this and just, erase this, erase this. Okay, A and A plus 2. And what they're saying here is that wherever A is, I don't know, I mean, maybe A is right here, okay? Maybe this is A right here, okay? And A plus 2 is like right here. So in this case, it kind of looks like A is like 29 and A plus 2 is like 31 or something. Well, all that really matters is the fact that A and A plus 2 are how far apart? 2. So that means the length of that interval is 2. Because since A and A plus 2 are both between 25 and 35, I just need to take a width of 2 over the width of the whole interval, which is 10 in this case. So that probability is 2/10. 2/10. Right? Same as it was up here. This right here happened to be the case where A was 33 and A plus 2 was like 35, 2 more than that, yeah? Okay, so there's that. Uniform distribution is fairly straightforward. We'll come back and revisit this in a couple of moments here, but let's move on. Just like we did in the case of the discrete distributions, we have the cumulative distribution function, which is the probability of being equal to or less than some value. Call it the CDF sometimes. And we use a capital F of x to denote the cumulative distribution function. So the cumulative distribution function at big F of x is equal to, which is the probability that capital X is equal to or less than x, is going to be the integral from all values below x all the way up to x. You integrate the density dy, and please be careful not to use the variable of integration. It would be bad if you wrote f of x dx, because x is actually in the upper limit of integration here. So you should write f of t dt, or f of w dw, or f of y dy, f of z dz. Just use a different variable of integration, otherwise you'll confuse yourself. Okay. So right here, for each x, capital F of x is just the area under the density curve to the left of little x. Okay, so that picture right there is just, okay, I have this density curve in blue, and the cumulative distribution function, capital F of 8, which is the probability of being equal to or less than 8, is just that area under the density curve up to 8. Yeah? That would be this, right? So because we would just integrate the density curve up to an upper limit of integration of 8. Okay, should be clear because we did this before. Like as x increases, capital F of x increases because the probability gets bigger and bigger and bigger that x falls below that x value. As little x increases, the probability of falling below that x value, if x gets bigger, is getting bigger and bigger and bigger. So that means it's going up from left to right all the time, and it's as x goes to infinity, the cumulative distribution function tends to 1. Okay, so that has a limit of 1, obviously, because the probability can't get bigger than 1, and it's always going up. So you're getting closer and closer and closer to 1. And if you let x go to minus infinity, the cumulative distribution function is going to 0. So, I mean, here's kind of a picture of what's happening here. Here's like what a typical cumulative distribution function looks like. So you put 1 on here like this. And what happens is the thing is always is always going up, but it kind of, asymptotically approaches 1. Okay, so it asymptotically approaches 1 as x gets bigger from left to right. And if x goes, and this thing is always going in an upward direction from left to right, but if x goes to negative infinity, you see that this thing is getting closer and closer to 0. And of course, because the cumulative distribution function is a probability, it's never smaller than 0, okay? So, so those are some facts about the CDF, okay? All right,